So without further ado, I would like to introduce the first speaker, Ryuya Nakamura, researcher at LayerX at the University of Tokyo, who will talk to us about formal verification and CBC Casper. Thank you.
Hello, good morning. I'll talk about formal verification and the formal verification of CBC Casper. I'm Ryuya from Tokyo, Japan, and working at LayerX. I'm working on CBC Casper for a few months, and previously working on KBM a bit and Viper. So first, what is formal verification? So formal verification is a kind of a way to prove properties based on math. And there are two kinds of formal verification. First one is the formal verification of programs, which is relatively popular in Ethereum community, like the formal verification of smart contract and formal verification of program in the client software. And today I will talk about the formal verification of protocols, of consensus protocols. To do formal verification, you first need to formalize the target. This is the example of KVM, and this basically formalizing the execution of EVM. So why people do formal verification? To do formal verification, you need to define everything in math. So this process of formalization makes it clear what is a target, what is a goal, what is the assumptions. So this reduces the miscommunication between researchers and developers and these humans. And in most cases, formal verification is performed in tools. There are a lot of tools to do formal verification, including general proof, interactive theorem provers like Coq, Isabelle, and domain-specific tools like K-framework. And this helps you to find the bugs because machine can check automatically whether the proof is correct or not. So I'll talk about my project of formal verification with CBC Casper. Quick introduction with CBC Casper. CBC Casper is a family of proof-of-stake consensus protocols defined by 5 parameters. And CBC stands for collect by construction, which means that every member of CBC Casper satisfies the same proof of asynchronous safety. So CBC Casper is originally written in really formal by Brad and other teacher and other workers. And my work is to define and improve the existing formalization in Isabelle. Isabelle is a proof assistant similar to Coq or Agda, and you can think of it as like an IDE for mathematical logic. I mean, you can refactor your proof, and you can use the lemmers, which is built in Isabelle, and Isabelle is relatively strong in automatic theorem proving. So this is the 5 parameters of CBC Casper in Isabelle. The V is a set of validators, and W is a weight mapping of validators. T is a threshold for certain Byzantine behavior, and C is basically a set of possible blocks, and E is called estimator, which is basically fork choice. And the bottom picture represents the restriction of these parameters. CBC Casper models the protocol by message and state. So validators send messages between each other, and the state is a local state, and it is a set of messages. And the message has 3 members. First one is sender, which is a validator who sends the message, and the estimate, which is the block which the message votes for, and justification. Justification is really important in CBC Casper, so I'll explain in this slide. Justification is the set of messages which the sender seen so far. So in this figure, the yellow block by validator B is justifying the green blocks. And in normal protocol execution, a validator must justify every messages he have sent so far. So justification is essentially the evidence of the fork choice. So the estimate, which is the block the sender vote for, must be the result of the fork choice. So the good point to have justification in messages is that you can detect these certain kinds of Byzantine behavior. Yeah, so the formal definition of valid message and state is a bit complicated, but there is two important points. The first one is that the validator must justify every messages which the other message justifies. And the second red statement is the enforcement of the fork choice. So this is a Byzantine behavior which can be detected by justification, which is called equivocation. So in this figure, the validator D, there's two blocks by validator D, does not justify each other. So it's equivocation. So you can detect these kinds of Byzantine behavior in CBC Casper. And this helps proof of safety and other things in CBC. State transition in CBC Casper is relatively simple. It's just a superset relation of states. And this is a formal definition of decision in CBC Casper. So in the traditional BFT consensus protocols like Tendermint and PBFT, validator make decisions on blocks which have 2 times of 2/3 of votes. But in CBC Casper, the decision-making rule is really strict because validator must make decisions which is proved to be true for any future state. So to actually detect these decisions, you need some heuristics like called safety oracle. So I'll explain what the proof in Isabelle is look like. This is asynchronous safety in CBC Casper in Isabelle, and the 3 line in the bottom is Isabelle proofs. So Isabelle have a lot of proof method, and the first line is basically unfolding the definition of decided, because Isabelle does not unfold definitions by default. The second line means that I want to use the lemma, which is already proved in another place. The third line is the automatic theorem proving method, which is METIS, and it using the built-in lemma. To be honest, I didn't find the last line of proof because we have automatic proof such. So in Isabelle does not always prove everything, but Isabelle sometimes help you to find some part of proof. This is a picture which Isabelle finds the last line of proof. So the previous definition of safety is a little bit too abstract. So we can instantiate the theorem to the blockchain context. This is safety in the context of blockchain, which means that there is no conflicting blocks which is agreed on by validators. So finally, I explain my work in progress work and the future works. The biggest one is that to prove the correctness of safety oracle. So as I explained, in CBC Casper, the decision-making rule is really strict. So every validator must detect the finalized blocks. And this is one kind of safety oracle called Greek oracle. In Greek oracle, validator try to find a set of validators which is called Greek. This is basically the validators who locked on the block. So liveness, every people talk about the liveness of CBC Casper, but my conjecture is that a creek eventually forms when the underlying chain converges. So from this observation, what we need to do to prove liveness of CBC Casper is that to prove the liveness of the underlying chain. So liveness in CBC Casper is essentially equivalent to the liveness of the underlying chain. So for that, we need to prove the convergence of LMD ghost because the default fork choice in CBC Casper is LMD ghost. So to prove these kinds of things in Isabelle might be a bit tricky, so I might use another way to prove this formally. Thank you so much.